Hi ladies. So this video covers the entirety of chapter 18, Radioactivity and Nuclear Chemistry. The first thing that we see in our chapter handout is the definition for radioactivity. So radioactivity is the emission of tiny invisible particles or energy, by unstable nuclei of certain atoms. So certain atoms, something's going on with their protons and neutrons that are causing these atoms to be unstable. So maybe they have a bunch of energy for some reason, which is making them unstable. So they need to let off some particles or energy in order to stabilize themselves. We're going to see a few different types of radioactivity, but first we need to talk about a few definitions that pertain to these types of radioactivity. Ionizing power, that is the ability of radiation to ionize other molecules or atoms. Ionize means that we are making an ion out of that molecule or atom, which means we are either taking away its electrons or giving it electrons, so giving it a positive or negative charge. That's what ionizing means. Penetrating power is the ability to penetrate matter. So is it going to bounce off something? Is it going to pass halfway through the thing? Or is it going to penetrate all the way through that object? So we will talk about each of those and how they pertain to our types of radioactivity. So the first type of radioactivity we are looking at is an alpha particle. How we are going to do the notation for alpha particle is like this. So 2 protons, that means we're dealing with helium, because helium is the element that has 2 protons, and 2 neutrons, which means we have a mass number of 4. So we have our element symbol, the number of protons in the bottom, so 2, and then our mass number up top. So an alpha particle is a helium-4 atom. Alpha particles, they are high ionizing, which means that they easily make the thing that they come in contact with, they're either stealing or giving it electrons, and low penetrating power. So these guys can be stopped with paper or clothes. So if you're wearing clothes, your clothes will prevent these alpha particles from coming in contact with you because they're relatively heavy and relatively slow. Because relatively speaking, they're kind of big compared to the other types of radioactivity that we'll talk about. So when we are doing nuclear equations, like we do in example number 1 and 2 in just a moment, we're going to be using the second box here in order to model what's going on. So we're going to take our parent nuclide, so whatever we are starting with, and we're producing a alpha particle, so a helium-4 atom, and then whatever is left. So we're going to do some either adding or subtracting, depending on what we're asked for in our nuclear equation. So we're following this pattern right there. So example number 1. So write the nuclear equation for the alpha decay of radium-223. So basically what we're doing here is we're taking radium-223. 223 is its mass number. Radium is number 88. Its atomic number is 88 protons. So with alpha decay, we're producing an alpha particle, so a helium-4 atom. And then whatever is left, we're subtracting them. So 223 minus 4 is 219 as a mass number. And then 88 minus 2 is 86. Element number 86 protons, is radon, the noble gas. So radium-223 is going to alpha decay into radon-219. All right, example number 2, we're going the opposite here. So what nuclide X, some element, decays by alpha emission, forming lead-212. So basically lead-212 is our product, like radium that we formed here. So we are technically putting lead-212 here as our product, plus an alpha particle, a helium atom, and that's going to give us what we started with, and that's what the example 2 is asking for. So that's what we're doing here. Lead-212, lead is number 82 on the periodic table, 82 protons, plus 4 mass number 2 protons. So 212 plus 4 is 216 as a mass number. And then 82 plus 2 is 84. So we got polonium 216 will alpha decay into lead 212. So we're just working backwards from example 1 that we did there. The next type of radioactivity, radiation that we're going to talk about is a beta particle. So beta particles are high energy electrons. They have intermediate ionizing power and intermediate penetrating power. They can be stopped with aluminum foil. They can also penetrate the top few layers of your skin. So if you come in contact with it, it's going to pass through the first few layers of your skin, but it will be stopped after a little bit. How we are going to do the notation for beta particles in our nuclear equations is like so. So electrons we typically abbreviate as like a lowercase e. Electrons have negligible mass. Their mass is super, super small relative to a proton or a neutron. So we are going to basically say that it's 0. Electrons have a -1 charge, so they don't have protons. So instead of putting the number of protons like we do here with helium, we're going to put the charge instead because they don't have protons. So instead we're just going to say we got a mass of 0 basically and a charge of -1 for our electrons. For these nuclear equations that we are going to write in example 3 and 4, we're looking at what's going on here in this diagram. So notice we're starting with a carbon-14 nucleus, and through beta emission, we have an electron, a beta particle is emitted from the nucleus, so that's leaving, and then a neutron is being turned into a proton. So notice how with beta emission, we're going from carbon-14 to nitrogen-14. So we are turning a neutron into a proton, so we are basically getting another proton, which changes us into another element, because elements, they have a specific number of protons for each of them. So beta emission, we're releasing a beta particle, and we're turning a neutron into a proton, so increasing our atomic number by 1. All right, let's look at example number 3. Write the nuclear equation for the beta decay of berkelium 250. So berkelium is 250, its atomic number is 97. So it is going to beta decay into a beta particle. So an electron, -1 charge, basically 0 mass. So we're not losing any mass really. So our mass number is going to stay the same, so 250, but we are gaining a proton because a neutron is turning into a proton. So we're going up 1 atomic number. So 98. Element number 98 is californium. So that is example number 3 there. All right, example number 4. Neptunium-237 nuclide is unstable and emits a beta particle when it decays. So write the balanced equation showing this decay and the new element formed. So Neptunium-237, its atomic number is 93. It is going to beta decay producing a high energy electron. So again with the -1 charge. Which means that we're turning a neutron into a proton and going up 1. So again, electrons have negligible mass, so our mass number isn't going to change, but we are gaining a proton, essentially. So plutonium is element number 94. So we are beta decaying neptunium into plutonium. Our next type of radioactivity that we're going to talk about is a gamma ray. Gamma rays are electromagnetic radiation with no mass. They are our highest form of electromagnetic radiation that we talked about in chapter 6, I believe. But these guys are super high energy electromagnetic radiations. They are low ionizing, but they are high penetrating. Basically, they can be stopped with 10 centimeters of lead or 30 centimeters of concrete. So I have a ruler here, 10 centimeters of lead is that. So relative to like this piece of paper, it's what, half of the piece of paper? Or 30 centimeters of lead, which is like 1.5 pieces of paper wide. And that's of concrete. So 30 centimeters of concrete, 10 centimeters of lead. That is a lot that's necessary in order to stop these guys. So these guys will pass right through your body and do a lot of damage because they are super high energy. Because they're energy, they're not particles. So how we're going to do the notation for gamma rays is we're going to use the Greek letter gamma. And then they're not particles, so they have zero mass. So it's not basically zero like an electron. These energy has zero mass here. And they don't have a charge, and no protons. So we're going to put a 0 down below, where we would either put the number of protons or the charge. So this is our notation for a gamma ray when we're doing our nuclear equations. All right, example number 5. Write the nuclear decay equation for radon-221 by alpha and gamma emission. So how we are going to specify that a nucleus is unstable with, or in the excited state, how I have written here, we're going to put a little asterisk, especially, we're going to use this especially with gamma emission. So radon-221, radon is element number 86 protons. If we were just looking at gamma emission, it would no longer be in the excited state because we've released a large amount of energy via gamma emission. So if we were to do by alpha decay as well, we are emitting a helium atom, so helium-4 atom, plus gamma energy, gamma rays. And then we're going to do some subtracting. So 221 minus 4 is 217. 86 minus 2 is 84. So basically we are looking at polonium. So radon-221 is going to alpha and gamma emission decay into polonium-217. So this is just via gamma emission. Here it is now via alpha and gamma emission. All right. Let's look at our next type of radioactivity. We're looking at a positron. So a positron has the mass of an electron, but a positive 1 charge instead of a negative 1 charge. This is how we're going to do the notation for a positron when we're doing our nuclear equations that we've been doing. So it's basically very similar to an electron, so we're still going to use the lowercase e. It has the mass of an electron, which is negligible, or basically 0, but a positive 1 charge instead of negative 1 here. What's going on here with our positron emission? So we have a positron emitted from the nucleus, it's just leaving, and a proton is being turned into a neutron. So basically we're losing essentially a proton. It is being turned into a neutron. So we are going down in our atomic number when we're writing these nuclear equations. So example number 6, write the nuclear equation for the positron emission of potassium-41. So potassium is element number 19. Its atomic number is 19 protons. Potassium-41 is its mass number. So via positron emission, so we're emitting a positron. So basically negligible mass, so we're not really losing any mass. So we're keeping the mass number 41s, but we are losing a proton essentially because it's turning into a neutron. So that means that we're going down 1 in our atomic number. Element number 18 is argon here. So positron emission, we're just going down 1 element on the periodic table, basically. All right. Our next type of radioactivity that we're going to look at is electron capture. So in this, a negatively charged electron is captured by a heavy, positively charged nucleus. So that positively charged nucleus is going to be attracted to these negatively charged electrons, obviously. And this is just going to result in a more stable nucleus for that already unstable, positively charged nucleus. So it's going to capture that electron in order to stabilize itself. In electron capture, we have a positive proton is converted to a neutral neutron. So a proton is being converted into a neutron. So we're going down in atomic number. Atomic number decreases by 1 and a different element is formed because the number of protons determines what element we're talking about. All right, let's look at example number 7. Right, the balanced nuclear equation for the decay of lead-2O4 by electron capture. So, if you were thinking about like beta particles, this is kind of the reverse of the electron or the nuclear equations we've been writing for beta particles, because we are not emitting an electron, we are bringing an electron into this nucleus. So lead-2O4, its atomic number again is 82. So we are bringing in an electron, which means that we are turning a proton into a neutron. So we are going down 1 in atomic number, we're losing a proton. So still basically same mass because electrons have very small mass. And then we're going down in atomic number. So element number 81 is TL. So that is what we are decaying into via electron capture with lead-2O4. We are not going to go through these exercises 1 through 6 in this video, but if you want to pause the video and check your answers that you did them correctly, go for that. But here are the answers. We're not going to go through the process of getting there, though. Okay, so we have a few different ways to detect radioactivity. So we can use a film badge dosimeter, we got Geiger-Müller counters, or scintillation counters. So these film badge dosimeters, these are worn by X-ray technicians and research scientists who work with radiation on a daily basis. Basically, these badges have film on them, and exposure to film from radiation. So radiation is bouncing off this film and it darkens the image. So once the image gets dark enough, those X-ray technicians, they can't work around radioactivity, anything with radiation, for a certain period of time until that radiation leaves their body, in order to keep them safe and not get certain types of damage from radioactivity, because radiation can cause cancer. Absolutely. So X-ray technicians, who their job is to work with radiation, we need to make sure we're not overexposing them, giving them radiation poisoning. So they're wearing these film badges, and once they get, the image gets darkened from exposure to radiation, they have to go home for an extended period of time. These Geiger-Müller counters, these guys detect alpha, beta, and gamma radiation. And basically there's argon gas in this little contraption. And when the argon gas is ionized via these types of radiation, it releases electrons. And these electrons are detected and heard as clicking sounds. So if you have watched any like movies with radiation, where radiation's like a big part of the movie, you might hear like these clicking sounds. That's probably from a Geiger-Müller counter. So they click a lot faster when there's a lot of radiation nearby. And then scintillation counters. So these guys detect flashes of light from ionizing radiation. That's just a little blurb to add to your notes there. So it's just another way to detect radiation. Student exercise number 8. So name a type of detector used to record the amount of radiation received by a person over a period of time. So it could be like the film badge dosimeter. It's not like a quantitative amount, it's more qualitative as the badge darkens. All right. The next thing that we are talking about is we are talking about natural radioactivity and half-life. So every element has a half-life. So every element is relatively unstable. Some are very, very unstable, and others are very, very stable. So the half-life is the time for half a sample to disintegrate. So let's say we start with 10 grams of a sample, and we want to know how long it takes to get 5 grams of that sample. So that length of time that it goes from 5 to 10, half of that sample, is our half-life. So these half-lives, we're going to do some calculations with these, but basically our half-life is not a linear graph. So it's not like after 2 times our sample is gone. We're taking half of whatever's left for that sample. So let's say we start with 1. After a half-life, we'll have 5. After another half-life, we would have 2.5. After another half-life, we would have 1.25. So going like that. I think I messed those up, but you get the point. So we are taking our last sample, dividing it by 2 for each half-life. So we get this curved graph here where we are converging, just getting really close to 0. Table 17.1 is interesting because it gives us some half-lives of certain nuclides. So uranium has a half-life of a lot of years, 4.5 times 10 to the 9 years. That is, I think that might be a trillion, or close to it. Carbon-14, its half-life is 5,730 years. So after 5,730 years, a 10-gram sample of carbon-14 will decay into 5 grams. Radon-220, its half-life is 55.6 seconds. So in less than a minute, a sample of 10 grams of radon will decay into 5 grams of that radon. TH219, its half-life is in the microseconds, 10 to the negative 6. So as you can tell, we have a wide range of half-lives that we see with our elements. An interesting one is bismuth. So bismuth, its half-life is longer than the age of the universe. So it is a very stable element and has very stable nuclei. So with these half-lives, we didn't wait or start measuring like 5,000 years ago a certain sample of carbon, and then like yesterday it's finally been to the point where half of our sample is gone. We can start with a certain amount of sample, and after a certain amount of time we can figure out how much of that sample is left, and do some calculations and projections mathematically to figure out, okay, so let's say a year has passed, and this much of our sample has decayed. So if I want half of my sample to decay, how long would that take? So that's what we're doing here. We're doing some projections and whatnot. So these are not always experimentally determined. So like the larger ones for sure are mathematically and theoretically determined, but these smaller ones, absolutely we can experimentally determine. All right, so in example number 9 and 10, we are going to do some half-life equations. So determining the half-life or how long has passed or whatever with these guys. If you go on to like upper division chemistry in college, you will see half-life equations. For our purposes here, we don't necessarily need equations. We're just going to do like a more conceptual process here. So let's look at example number 9. So how long does it take for 1.8 mole sample of TH227. We're given a half-life of 1.8 years to decay to 0.225 moles. So basically we're figuring out how long it takes to get from 1.8 to 2.25. So what we're going to do is we are going to utilize this half-life. Half-life means that we are decaying our sample by half each time we pass through. So what we're going to do here is we are going to divide our sample by 2 each time. So 1.8 moles divided by 2 is 0.9. So that half-life is 1.8 years. So 1.8 years have passed to get to this much. We're not at 2.25 yet, so we need to keep going. So half of 0.9 is 0.45, so another 1.8 years has passed to get to here. Still not to 2.25, so we need another half-life. So another 1.8 years to get to 0.225. So 3 half-lives have passed here, so 1, 2, 3, in order to get to 0.225. So 3 times 1.8 years is 5.4 years. So that's how long it takes for this sample here to decay to that amount. So we're just halving each time we go through a half-life, each time we go through a cycle. All right, let's look at example number 10. Iron 59 can be used to study the intestinal absorption of iron. If 6 grams of the isotope is present when purchased, how many grams of the isotope would be present 94 days later? How many grams remain after 141 days? And we're given the half-life. Half-life is iron 59 is 47 days. So what we need to start off here is we need to figure out how many half-lives have passed in 94 days. So we're going to do 94 days divided by 47 days, our half-life, and that gives us 2. So 2 half-lives have passed after 94 days. So we're taking our initial 6 grams that we started with, we're taking it by half. So 47 years pass, and we're left with 3 grams. And then we have to do that again for 2 half-lives. So another 47 years have passed, and from 3 grams, we are left with half, so 1.5. So after 94 days, we're left with 1.5 grams. We also want to know after 141 days, so we're going to take 141 divided by 47 days, and that gives us 3 half-lives. So we've already done 2 here, so we just need to do 1 more. So divide by half again, and we get 0.75 grams are left after 141 days. So again, if you go off into college and do chemistry, you'll see actual half-life equations, but for our purposes, we're not. You don't need to know it. For these student exercises here, however, there is one that I do show the half-life equation here. So here are the answers for these student exercises. I'm not necessarily going to go through all of them, though, but for exercise number 7, how old is a bottle of wine? If the tritium activity is 25% that of new wine. So basically, we're taking 100 minus 25% as a decimal, so 0.25. That is what is remaining, so 0.75. And I realized that I did the work wrong. This should be 0.75. That's what's remaining. This is the half-life equation. So our half-life times a certain number of half-lives is equal to what's remaining. So in order to isolate n, we have to take the natural log of what we have on this side and then the natural log of this guy here, which is what's over here. Again, this should be 0.75 instead of 0.25 over that half here. I believe that should be like 3 or 4 half-lives. And at that point, you should take the half-life, that 12.2 years times however many half-lives that is, and that should be 14.4, actually. So we have the natural log of 0.75 divided by natural log of 0.5. So this should be times 2. Okay, yeah. So yeah, that's basically what we're doing there. Okay, so I'm going to skip 8 and 9. And you can check your answers there if you want the practice. Okay, the next thing we're talking about is radiocarbon dating. So we can use knowing the half-life of carbon-14 and these concepts here, we can figure out the age of certain things. So we can figure out how old a dinosaur fossil is, how old a tree is, based on the carbon-14 that's decayed. So in living organisms, there's a constant concentration of carbon-14. So by eating and breathing and whatnot, we are constantly replenishing our carbon-14. But once we die, there's nothing replenishing our carbon-14, so it is just going to keep decaying. So based on how much has decayed and how far along in the decay process it is relative to its half-life of 5,730 years, we can calculate how old a thing is. Obviously, it's an estimate, but it's a pretty useful and accurate estimate. So that is what we can do with these radiocarbon datings and these half-lives. That's a practical use. With induced radioactivity, we have transmutation. So transmutation is the conversion of one element to another by an induced nuclear reaction. So basically, we're going to bombard a nuclei with an atomic particle, and the nuclide is converted to a different element through some type of radiation, whether it's any of the ones that we've talked about. So like alpha decay or whatever. Kind of history of science lesson here. A lot of the past chemists who worked in the field of chemistry before it was like a really established field, they were trying to transmutate other elements into things like gold or silver to make themselves rich. So we can transmutate other elements into gold. It is just very expensive and time consuming, and it is not cost effective in the least. So that's why we don't do it, but we can. So using certain types of nuclear reactions, like forcing these elements to undergo some type of nuclear decay or whatever, we can transmutate elements into other elements. Example number 11 is another practice with nuclear equations. So write the equation for the bombardment of nitrogen-14 with an alpha particle produce hydrogen-1, which is a proton, and oxygen. So basically, we're taking nitrogen and this helium-4 atom, we're adding up the mass numbers. So total, we should get 18. So total 18. And then for our protons, total, we should get 9. But keep in mind, a hydrogen-1 atom is a proton. So we have a mass number of 1 and a 1 proton. So one of those 18 mass numbers need to go with hydrogen, and then one of the protons, of the 9 protons, goes with hydrogen as well, which means what's left over, 18 minus 1 is 17 as a mass number for oxygen, and then 9 minus 1 is 8, and element 8 is oxygen. So that's how we're doing example number 11, like that. Okay, next what we're talking about is fission. Is fission, and it's in regards to the atomic bomb and its application there. So fission is we're splitting a large atom into smaller atoms. So in our nuclear power plants, this is the type of nuclear reaction that is going on. So these fission reactions, we're taking larger atoms, putting in a certain amount of energy, getting a reaction started, and that's going to generate energy that we utilize for electricity, that power our cities, our homes, and whatnot. So an example here is uranium-235. So that's going to split via fusion, and it's going to release energy, and we can capture that energy in the form of electricity. So many unstable heavy nuclei spontaneously decay by nuclear fission. And so basically what we do in nuclear reactors is we just utilize that fission, that decay. This process has a domino effect, so fission. This is known as a chain reaction. So at the top of the next page, we talk a little bit more about what that means. So chain reaction, when fission reactions initiate more fission reactions and become self-sustaining. So this diagram here is basically what's going on. We start with some unstable large nucleus. We have to somehow get it to split up. So fission there. And it's going to split up into two. Those two are going to go and hit other larger nuclei, and then those guys are going to split up, and eventually those guys are going to split up, and so on, which causes this chain reaction of these huge releases of energy, really. Okay, so we have a few different things that we're talking about here. So about 50 kilograms of uranium-235 is needed to produce a self-sustaining reaction. So most of our nuclear power plants utilize uranium-235 because it's a self-sustaining reaction. Only 0.7% of naturally occurring uranium is fissionable. You have uranium naturally occurring in soil, everywhere on Earth. But only 0.7% of it can we actually utilize for these fission reactions. For uranium enrichment, we use uranium enrichment, to obtain a chain reaction. So that 0.7% is made to about 3%, and we do that by enriching it, reacting it with fluorine gas. So after it's been enriched, it causes an incredible release of energy, and we have used that energy historically in the past with World War II to create an atomic bomb. So the Manhattan Project was basically a secret government project of creating this atomic bomb. And basically we revealed it to the world that we were able to create an atomic bomb when we dropped it on Hiroshima in World War II and killed nearly 100,000 people because of this monstrous release of energy. So basically the project cost us $2 billion about, and it cost, I think, around 80,000 lives in World War II when we dropped it on Hiroshima, which is a very terrible thing to do to people. Okay, so example number 12. So again, we're writing a nuclear equation. So this is a spontaneous decay of californium-252. Forming barium-142 and then MO-106. We're producing 4 neutrons and energy. So that energy could be in the form of gamma radiation, but this probably is not gamma radiation. We're going to take californium-252. It's number 89, so 98 protons. And we're decaying into barium-142. Barium is number 56 on the periodic table, so 56 protons. MO-106, MO is number 42 on the periodic table. 4 neutrons. Neutrons have a mass number of 1, and then we're producing energy. So if my math is correct, this 142, 106, and 4, so 1 times 4, mass number 4 at that point, should equal 152, I believe it does. And then 56 plus 42 should give us 98. So that's how we're doing that nuclear equation. The next thing we're talking about is nuclear fusion. So fusion is the nuclear reaction that occurs in the sun. So fusion is when two lighter atoms, so not, we're not talking about photons, so like light particles, we're talking about less heavy. So lighter atoms combine to form heavier atoms. So with the sun, we are it is combining hydrogen and helium into a bigger atom. This produces an incredible amount of energy. So it releases more energy than fission. And that is basically why we can feel the energy and see the energy from however billions of light years away the sun is. So we can see that energy through light. Light is a form of energy, and heat. Like we can feel the sun's heat from that distance, however many light years away we are from the sun. Fission reactions are more difficult to initiate than fusion. Fusion is more difficult to initiate than fission because we need over 10 billion degrees Celsius in order to overcome these repulsive forces of nuclei. So nuclei don't necessarily want to be really close to each other at all. They would rather break apart and separate via fission. But in the sun, we have that incredible temperature that is able to fuse the hydrogen and helium atoms into a bigger atom. So again, it releases more energy than fission, and it produces little radioactive waste. In terms of fission, with our nuclear power plants, that creates radioactive waste that we, as a society, have to figure out the best way to dispose of that. And there's really not a good answer to that. But yeah, so with fission, we have very little radioactive waste. Okay, so we have a few different potential energy sources that if we can fuse them with other things, we can produce a lot of energy. So deuterium and tritium. Deuterium is an isotope, so both of them are isotopes of hydrogen. Deuterium has a neutron, so hydrogen already has a proton, so that would mean that deuterium has a neutron as well. So 1 + 1 is equal to 2 here. Tritium, again, has 1 proton for hydrogen, and it would have 2 neutrons. So we're just changing the number of neutrons. That's what an isotope is, and we have talked about that. I can't remember in which chapter. But if we were to be able to use these guys in fission reactions, we would have, for example, 1 mile cubed of seawater could provide more energy than all the oil reserves in the world. And that is an incredible amount of energy if we are able to utilize them via fusion reactions. All right. So our next thing that we're going to talk about is the effects of radiation on life. So in table 17.3, we have doses of radiation that, and their probable outcomes over here. So take a look at those. Those are pretty interesting. But in general, we could get acute radiation damage. So that could be in the form of burns, like skin burns. Increased cancer risk, so that high energy radiation could pass through your body, and that could give your cells way more energy than they should have, which causes them to become cancerous and just grow like crazy. We could also see genetic defects via form of DNA mutations, so maybe those particles or energy, like especially gamma radiation, passes through your DNA. It would obviously cause damage, probably splitting apart your DNA because of the energy that DNA molecule now has, which would cause DNA mutations and obviously genetic defects at that point. So those are some of the effects of radiation that you might see. Okay, student exercise 13. What makes ionizing radiation hazardous to living things? So basically, high high energy radiation disrupts cell growth, causing cells to multiply unchecked. And that is cancer. That is our definition of cancer. Okay, however, so we've talked about how radioactivity can be useful, pretty bad, but here's where it is useful. So radioactivity in medicine. We can cause certain atoms to be radioactive. We call these isotopes. And we can track where those radioactive isotopes are in the body by scanning their path, basically. So that's super helpful for figuring out, like, for anatomy, figuring out the pathway of, like, veins and whatnot. We can track where that radioactive isotope is going. And radiotherapy. Okay, so exercise 14 talks about that. But radioactive iodine-131 is used in therapy for the treatment of cancer of the thyroid. What happens to the cancer cells of the thyroid? So we're talking about thyroid cancer. Your thyroid needs iodine in order to function properly. That's why our salts, so like if you buy salt at a grocery store, you'll probably see that it's iodinized salt. It's enriched with iodine in order to make sure we get a certain amount of iodine in our diets. So basically, we're taking iodine that we're going to consume and we're making it radioactive. And basically what happens there is we ingest that radioactive iodine, and that iodine goes to our thyroid and is absorbed by the thyroid. And once it's collected there, it's going to start destroying the cancer cells that are nearby, just like breaking things apart. Radioactivity, so like radiation therapy for like cancer patients and whatnot, radioactivity doesn't know the difference between a cancerous cell and a normal good cell, which is why with radiation therapy, we need to focus in really, really specifically onto what we're targeting with this radiation. Otherwise, we're going to damage a lot of good surrounding cells that we don't want to kill off, obviously. So we're just going to focus, like really focus in on a certain point and kill those cancerous cells with radiation in that sense. And that is the end of chapter 18 and the end of our packet.